On January 16, 1943, the SS Schenectady rested peacefully alongside the pier in Portland, Oregon. This Liberty ship was practically brand new, only about 10 weeks out of the Kaiser shipyards. No hostile forces endangered it, no fierce weather assaulted its frame. The morning air hung serene, the harbor waters unmoving. Suddenly, a piercing snap resounded over the docks. In an instant, the whole ship split wide open down the middle. The structure tore from top to bottom as though cut by some unseen force. Crew members rushed about in chaos as the forward and rear parts drooped apart. The vessel's spine had snapped, all while securely moored at the wharf. The Schenectady faced this fate in isolation. That winter, the SS John P. Gaines likewise shattered in tranquil conditions. The SSSO Manhattan, a T-2 tanker assembled with the same approaches, developed such deep fissures that her team fled the ship in alarm. From 1943 to 1944, over 2,500 Liberty ships experienced major structural breakdowns, rips in plating, breaks in decks, devastating separations. At minimum, 19 ships divided entirely in two. 3 others disappeared entirely on the ocean, crumbling away so swiftly they never managed to broadcast Mayday calls. These incidents stemmed not from combat losses. They were instances of vessels essentially self-destructing. The United States had staked its all on the Liberty Ship Initiative. Following Pearl Harbor's plunge of America into full-scale conflict, the country urgently required freighters, dozens upon dozens, and quickly. Conventional ship construction demanded 8 months for each one. The Maritime Commission had no time for such delays. Henry Kaiser, a businessman with zero prior experience in shipbuilding, offered a bold proposition. Mass-manufactured cargo carriers put together like cars emerging from production lines in mere weeks, not months. His facilities in Richmond, California, adopted groundbreaking methods, favoring welding over riveting, pre-assembled components over hand-fitted pieces. Production flows drawn from Detroit's automobile plants. By the end of 1942, Kaiser's operations were delivering Liberty ships on average in 42 days. The publicity apparatus hailed this feat of industry. Film clips highlighted Rosie the Riveters, though they were welders in reality, shaping metal sheets into ocean-worthy hulls at unbelievable paces. The SS Robert E. Perry claimed a milestone that November 1942 completed from keel down to splash in just 4 days and 15 hours, sparking nationwide applause. Allied merchant fleets, hammered by U-boat assaults, at last received a flood of support across the Atlantic. Yet these ships began to fail, not from strikes by torpedoes or turbulent waves, but abruptly and disastrously during what ought to have been ordinary circumstances. Ship designers stood perplexed. The joints appeared sturdy. The metal adhered to standards, the plans derived from reliable British designs. Still, Liberty ships were splintering apart like fragile china. The fissures usually originated at abrupt angles, access hatches, armament platforms, the boxy contours of the exterior. Once underway, a fissure would tear through the joined metal sheets at alarming velocity, at times spanning a ship's full length in mere moments. The Maritime Commission launched urgent probes. Material scientists scrutinized damaged parts with magnifiers. Analysts double-checked load assessments. Marine examiners poked into breaches armed with gauges. All hunted for the root cause. Substandard alloy, flawed joins, blueprint errors, lax oversight. Meanwhile, more ships kept coming apart as panels conferred. Seamen developed a deep fear of their floating workplaces, aware the shell underfoot could rip open unexpectedly amid icy North Atlantic swells. The triumph of rapid fabrication had morphed into a seafaring horror, with no one able to pinpoint why these speed-built ships were faltering so prolifically. The solution emerged from an improbable quarter, a line worker handling welds who had no business challenging expert choices. Bessie Hamill pulled the night shift at Kaiser's third yard in Richmond, one among countless women who surged into the yards once the men deployed abroad. For 8 months she'd been fusing hull panels, giving her ample time to spot what the specialists seemed to miss. Night after night, she observed her crew applying welds to huge metal slabs in an order that defied all logic. Hamill noticed operators commencing at the borders of sheets and progressing toward the middle, or kicking off at a seam start and plowing right through to the finish. As the joins hardened, the material shrank, tugging and bending the slabs. She could witness the tension mounting, observe the alloy twisting beneath her flame. With each segment sealed and the team advancing, they essentially sealed that strain into the framework forever. It resembled cinching the hub fasteners on an auto rim prior to the perimeter ones, a sure path to distortion and collapse. Her supervisor brushed off her worries. After all, she welded. She didn't design. The routine stemmed from the technical team, experts with university educations and shipbuilding credentials. Hamill refused to drop it. In November 1943, she demanded a sit-down with the yard's foreman, defying the established hierarchy in a move that risked her job. Armed with examples, test panels she'd fabricated off the clock employing various welding orders, she presented her case. Certain pieces displayed obvious buckling and clear signs of strain. In contrast, those assembled starting from the core and expanding systematically lay even and precise, with hardly any warping. The foreman remained doubtful, yet curious. One decided to monitor the assembly line on Hamill's overnight rotation. His first-hand view validated her findings. The welders were, in effect, inflicting damage on the metal, imposing strains that the plates would endure throughout their operational lifespan. Each successive weld introduced lingering pressures as it cooled. The building order caused these tensions to build up and focus at particular spots, especially around hatch corners and other vulnerable areas prone to stress buildup. Upon encountering the icy waters of the North Atlantic, the plates turned fragile. This trapped internal strain, coupled with the material's brittleness, set the stage for sudden, devastating breaks. Hamill's approach was straightforward yet profound. Begin welding at the heart of each panel and proceed outward, letting tensions flow to the periphery instead of piling up centrally. Switch between welding spots to avoid excessive heat in one region. Avoid finishing seams in extended, unbroken passes. Opt instead for a methodical pattern that spread out the cooling-induced strains uniformly. These ideas weren't groundbreaking advances in metal science. They stemmed from hands-on experience by a worker who handled the material daily, sensing its shifts beneath the flame and understanding the repercussions. By the end of 1943, her ideas had escalated to Henry Kaiser personally. He confronted a harsh dilemma. The Liberty Ship Initiative was already facing intense oversight from Congress due to the rampant cracking issues. Owning up to the assembly order rather than flaws in the metal or joint quality, as the core issue implied that all prior vessels carried inherent weaknesses embedded in their frameworks. It would require halting output briefly to instruct thousands of welders anew. It would necessitate overhauling the whole fabrication workflow. Yet, it also offered a chance to resolve the splitting problem that jeopardized the nation's complete sea transport network. To his merit, Kaiser acted decisively. He greenlit prompt trials of Hamill's concepts, halting a full base segment mid-production for a trial rebuild. Experts in metallurgy and design, who had devoted months dissecting wrecked vessels, now deferred to an evening shift fabricator without any formal academic background. The outcomes were both condemning and transformative. As Kaiser's specialists scrutinized panels made via standard procedures against those following Hamill's strategy, the contrast was quantifiable and striking. Instruments measuring lingering strains revealed that conventional joints held pressures over 30,000 pounds per square inch, focused at critical junctures. Hamill's ordered panels spread those forces over wider zones, with maximum levels just topping 12,000 psi. The base metal remained the same. The joints showed no chemical variances. Solely the sequence of steps differed, but the overall durability leaped ahead in ways the specialists at first dismissed as implausible. The mechanics of the breakdowns at last came into focus. Steel isn't an inert substance. It forms a crystalline lattice that reacts vividly to thermal shifts. When fabricators guide a flame across a joint, they generate a hot spot surpassing 2,500 Dadodrik eV. The material swells sharply in that localized area. During cool down, it shrinks, yet the adjacent cooler sections resist this pullback. This leaves enduring pulling forces embedded in the framework, persisting unless the welding pattern permits their even dispersal. Liberty ships were plagued by what specialists term brittle fracture spread. The carbon steel in their exteriors, specified for marine construction, held up fine in temperate seas but shifted perilously in the North Atlantic's sub-zero chill. Under about 40 F, the material's pliability vanished. Typically, alloys handle loads by yielding a bit, flexing instead of snapping. Chilled steel forfeits that resilience. It turns rigid, resembling brittle ceramic more than the resilient stock shaped in California's temperate docks. When such rigid metal encounters focused internal pressures at an acute angle, like the straight rim of a loading port, natural forces assert themselves with ruthless speed. A tiny fissure begins. In pliable metal, it would halt, soaked up by the substance's give. In rigid metal underpull, the fissure races unchecked. The pent-up energy from those internal strains drives its advance. Angular edges serve as force amplifiers, intensifying the immediate pressures multiplied by factors exceeding 3 times. The fissure propagated rapidly, at times surpassing the sound barrier within steel, surging across the vessel's shell before partitions or reinforcements could halt its advance. In retrospect, the SS Skenktedy's rupture was entirely logical. Constructed during the onset of winter, she had been joined using welding patterns that amplified lingering tensions. Her framework bore tens of millions of pounds of pent-up strain. As the Portland dawn fell to 28ers, the metal turned fragile. A tension buildup at a hatch edge sparked the initial split. That split traced an unobstructed route via unbroken welded deck panels. Absent any riveted joints to impede it, no tension-dissipating barriers to impede progress. The break devoured the vessel in mere moments, unleashing years of accumulated force in a single devastating collapse. Conventional riveted vessels avoided such issues, highlighting the apparent doom tied to welding methods. Riveting creates inherent breaks in continuity. Individual plates fastened by rivets act as isolated components. Any fissure beginning in a single panel encounters a riveted boundary and halts. The layered panels and mechanical connections form built-in barriers against crack progression. Welded vessels form seamless holes. A flaw in one section can propagate unchecked across vast stretches of joined seams. The very productivity that allowed quicker assembly of welded ships also rendered them prone to breakdowns unseen in riveted ones. The Liberty ship's angular layout worsened the vulnerability. British naval designers had opted for those abrupt angles to simplify freight handling. No one anticipated that such acute inner edges would amplify stresses, intensifying external forces by massive multiples. Each swell that bent the structure directed force surges to those edges. Paired with leftover welding strains and fragile metal, those points evolved into fracture origins, poised for disastrous rupture under ideal triggers. Henry Kaiser grasped the implications of the trials for his operations and the wartime push. Come January 1944, he reached a pivotal choice that could affirm his manufacturing overhaul or brand him a hasty opportunist responsible for dispatching countless seamen aboard faulty crafts. He mandated a full suspension of Liberty ship assembly at Richmond Yard 2, redirecting efforts toward a fresh vessel type, the Victory ship. Far from a simple tweak, this represented a thorough overhaul drawing from Bessie Hamill's welding insights and the painful wisdom etched in shattered hulls spanning 2 seas. The risk was immense. Liberty ships remained in urgent demand. U-boats had sunk more than 2 Allied cargo carriers since 1939. The European assault, yet to unfold in early 1944, demanded the grandest seaborne supply endeavor ever conceived. No vessel could be spared. Still, Kaiser wagered he could adopt Hamill's ordered welding approach, reshape the structure to avoid tension hotspots, upgrade the metal quality, and sustain the astonishing output rates. Rivals deemed him deranged. Lawmakers honed their probes, poised to condemn him should output falter. Kaiser's team reverse-engineered from the breakdown zones. All sharp angles in the Liberty blueprint were supplanted with curved junctions. The hatch portals, sources of numerous splits, were reconfigured with ample curves to diffuse the force amplifiers, converting routine pressures into brake starters. Deck and side plating gauges were reassessed, not for extra robustness, but to align strain flows with the revised joining orders. Support girders were shifted to harmonize with innate tension release areas instead of clashing with the welding layout. The material underwent transformation too. Kaiser's material experts prescribed a novel grade boasting better cold weather resilience. Carbon levels dipped marginally while manganese rose. Modest nickel inclusions, costly and reserved for tank plating, were advocated after proof showed that 0.25% nickel vastly boosted the metal's defense against snap failures. The shipping authority resisted the expense until Kaiser supplied figures revealing that averting a single vessel's demise would offset the premium metal for 50 units. By March 1944, the enhanced metal standard gained clearance. Next followed the enormous effort to reskill the labor force. Richmond facilities housed over 90,000 personnel by early 1944. Countless were welders trained in brief intensive sessions, gaining only the basics to produce linear seams at rapid paces. Now they required knowledge of ordering, strain mitigation, and heat control. Kaiser set up training centers on site, drawing seasoned welders like Hamill from duties to instruct. Each welder got a labeled order sheet for every hull segment. Weld 1 in this spot, 2 in that, adhering strictly to the mandated sequence. The pre-assembly process grew more extensive significantly. Instead of fusing extensive panels in areas where sequencing proved hard to manage, the planners at Kaiser divided Victory ships into compact modules built within specialized workshops. For instance, a bow unit could incorporate up to 50 distinct pre-assembled parts, each joined under precise conditions with ideal welding orders, followed by heat treatment in furnaces to relieve stresses prior to the ultimate integration. This segmented method allowed welders to proceed from the middle of every compact unit toward the edges, just as Hamill had illustrated, free from the limitations of constructing an entire hull at once. Doubters found grounds for criticism when the initial Victory ship keel was set in February 1944. The build required 18 days, lagging behind Liberty ship benchmarks. Kaiser's facilities were no longer pulling off wonders, they were constructing vessels at simply notable rates. The next Victory ship required 16 days. Detractors proclaimed the initiative a flop, evidence that superior quality and rapid pace couldn't coexist. Kaiser dismissed their views. He focused on fracture examination records beyond mere build durations. The initial pair of Victory ships revealed no stress fractures during after-build checks, not fewer fractures, none at all. Come April 1944, Richmond Yard 2 had evolved into a meticulous dance of metal, flames, and workforce synergy that would have appeared inconceivable just 2 years prior. The site no longer resembled a conventional shipbuilding dock. It looked more like a vast manufacturing facility, with separate production areas supplying a core fitting zone where ship bodies formed at astonishing velocities. Kaiser had adapted Henry Ford's conveyor belt idea, though here the workforce cycled through fixed build positions at set intervals, rather than shifting the item itself. Operations kicked off in the preliminary fabrication buildings, huge enclosed spaces where joiners handled hull pieces limited to 30 feet in any direction. Every piece came with a dedicated procedure guide. A base panel unit, for example, demanded 47 specific joins, labeled and marked by hue. Joiners began at spot 1, invariably the central point of the unit, progressing in a curving or spreading layout. Overseers patrolled the area with verification lists, confirming no one jumped steps. Following each set of 10 joins, the unit entered a tension-easing furnace, warmed to 2100 degrees and gradually chilled. This tempering step let the metal's internal lattice unwind, releasing lingering tensions before they built up to hazardous degrees. The metal stock itself showed up already trimmed and molded from mills retooled expressly for Victory ship output. In contrast to Liberty ships, where on-site crews trimmed and formed sheets, Victory elements arrived primed for swift integration. Arched forward units arrived shaped to precise measures. Floor panels featured pre-punched fastening spots for interim securing. Structural ribs were pre-joined units. Such upfront labor in regulated plant settings removed uncertainties and guaranteed uniformity over countless parts. Fitting on the slipways pursued a starkly altered order compared to Liberty methods. Rather than initiating at the base and rising layer by layer, Victory ships came together from sizable units developed concurrently. The power plant area, storage compartment units, forward and rear ends, all progressed side by side, then hoisted via enormous overhead cranes and placed in one unified maneuver. On May 12, 1944, Yard 2 pulled off its boldest fitting operation to date. 17 key units, accounting for 85% of a full body, were set and adjusted in merely 11 hours. Joiners then linked these units applying the identical middle-to-edge patterns, though now they merged pre-tempered pieces instead of creating tense ones anew. The 5-day schedule materialized via unyielding refinement of each moment. Evening crews staged supplies for morning teams. Dedicated squads handled only verification of positions and join integrity, spotting mistakes early to prevent spread. Portable hoists followed planned paths, supplying parts to join areas inside 5-minute slots. Joiners operated in shifts, 30 minutes active with the tool, 10 minutes break, sustaining steady standards without the slip-ups from exhaustion that hampered extended join marathons. Kaiser introduced his version of the essential route technique, monitoring which steps created holdups and which could advance concurrently. If rib placement ran early but conduit installation trailed, he redirected personnel on the spot, keeping equilibrium through all build stages. Each holdup, each schedule drift got recorded and scrutinized. Daily dawn sessions assessed the last shift's results, pinpointing fixes before minor issues escalated to major setbacks. The milestone arrived on June 27, 1944. The SS Benjamin Warner Victory ship, hull number 23, finished from keel setting to water tests in 5 days and 11 hours. Not a basic test vessel, but it was a comprehensively outfitted battle-prepared freighter boasting protective weaponry, intact power grids, an operational propulsion area, and each weld, replacing the old rivets, carried out according to updated stress mitigation standards. The vessel showed no fissure breaches. Post-assembly evaluations indicated strain metrics stayed within standard functional bounds. During its initial trial voyage, the Warner excelled seamlessly amid harsh seas that might have shattered initial Liberty vessels. This 5-day build Victory ship went beyond mere rapidity. It embodied a thorough overhaul of fabricating intricate machinery when technical theories meshed with real-world assembly needs. Insights from Bessie Hamill had sparked a broad overhaul in mass production shipbuilding. The Victory ships produced via Kaiser's revamped assembly process marked a profound shift from their Liberty forerunners. Though onlookers might spot comparable freight carriers with matching roles, the variances started at the atomic scale and permeated all facets of engineering and fabrication. Liberty ships served as hasty interim fixes, whereas Victory ships offered refined designs tackling each vulnerability etched in the sacrifices of mariners whose breaking keels plunged into icy Atlantic depths. The enhanced metal formula was pivotal. This novel compound, termed killed steel due to aluminum inclusion in the process to eliminate oxygen, exhibited markedly superior resilience in frigid conditions. Lab experiments indicated the shift point, where metal changes from pliable to rigid had fallen from roughly 40 degrees Fahrenheit in Liberty metal to around 5 degrees. That 35-degree drop ensured Victory ships kept their formable integrity in environments that rendered Liberty casings brittle husks. The added expense came to 8% per ton, yet the reliability boost defied quantification. All framework elements embodied fresh insights into strain buildup and fracture spread. The curved hatch edges, appearing as a subtle visual tweak, cut localized strain foci by more than 60%. Computations revealed that the acute 90-degree angles on Liberty ships amplified hull pressures by 3.5 to 4 times the baseline. The Victory ship's ample curves limited those amplifiers to under 1.8. In real-world scenarios, an ocean surge that might spark a split in a Liberty hull simply bent a Victory ship's shell within safe deformation thresholds. The plating was fitted with inherent fracture-stopping elements integrated into the build. Instead of unbroken seams stretching for hundreds of feet, Victory ships featured bolted joints at key spots. These mixed fastening zones created deliberate breaks, spots where an advancing split would encounter a physical barrier and dissipate force, possibly halting short of devouring the whole frame. The approach acknowledged potential starts of flaws, but built in layered safeguards against total spread. This was proactive design, anticipating breakdowns instead of banking on flawlessness. Key support ribs were reinforced in high-tension zones, forming backup stress routes. Should one rib fracture, neighboring ones could shoulder the burden until dockside fixes. Liberty ships lacked any such backups. One rib's breakdown typically triggered chain reactions as forces shifted to nearby strained parts. Victory ships endured hits that would doom a Liberty and still function, crawling back to harbor on impaired yet viable frameworks. The welding order derived from Hamill's findings was formalized into exhaustive guidelines dictating every connection across the vessel. The instruction guide spanned hundreds of pages, detailing not only the order but also heat oversight between applications. Welders were trained to track the temperature of the underlying material during intervals between layers. Should the metal surpass 400 degrees, operations paused for passive cooling. This avoided the escalating thermal accumulation that warped Liberty builds, where crews often pressed on along extended lines, overheating the alloy into twisted, tension-laden shapes. Oversight standards grew meticulous. Each finished seam underwent magnetic particle scrutiny, a method using ferrous dust and fields to expose tiny fissures undetectable visually. Sound wave probes assessed inner seam soundness, verifying complete fusion without concealed gaps. Radiographic scans reviewed vital framework seams, generating lasting image archives of seam reliability. Vessels weren't commissioned without verifier approval that all seams complied with criteria. Early rejection figures were steep. About 15% of seams in the initial Victory ships didn't pass checks. However, crews adapted swiftly. By mid-1944, rejection levels failure rates for Liberty ships had fallen under 3%, thanks to enhanced training initiatives and the straightforward new guidelines. This success was evident in real-world performance. From June 1944 until the conflict concluded in August 1945, a total of 531 Victory ships were commissioned. None experienced a total hull rupture. A few instances showed small fissures in select hulls, areas of strain that routine checks identified prior to any spread. Those fissures got fixed with identical stress relief welding methods, allowing the vessels to resume duties promptly. The difference compared to Liberty ships was stark and condemning. The vital tally of lives preserved and assignments fulfilled on Victory ships as opposed to Liberty ships unfolded over two vast seas during 1944 and 1945. This was etched in the survival of personnel and the success of operations that prior designs would have turned into tragedies. Take the SS Wanda Fuka, a Victory ship which struck a mine near Okinawa in April 1945. The blast ripped a 20F tear in her side beneath the water level. The team braced for the rapid crack extension that doomed Liberty ships. Yet the break halted right at the initial riveted seam. She reached harbor on her own steam, underwent fixes in 6 days, and went back into action. By comparison, the Liberty ship SS Richard Hovey endured a similar mine hit in February 1945, split along her length for more than 90 ft, snapped her backbone, and went down in 14 minutes, claiming 37 sailors. The supply chain for the Pacific theater would have collapsed without the dependability of Victory ships. Come June 1944, U.S. troops were advancing through the Central Pacific, heading for the Philippines and eventually Japan. Every island hop demanded billions of pounds of materials transported over thousands of ocean miles. Liberty ships managed the trips, yet their inherent weakness led to lighter payloads in stormy conditions, reduced velocities to ease hull strain, and the ever-present danger of sudden breakup remote from help. Victory ships carried maximum cargo at their intended 15-knot pace, 3 knots quicker than Liberty ships, across typhoon-heavy zones, free from the dread that chilly nights and choppy waves might tear them open. The figures painted the picture. From the D-Day landings in June 1944 to VJ Day in August 1945, Victory ships transported more than 18 million tons of goods without a single structural loss. They navigated North Atlantic groups where seas often chilled below 35 degrees, environments that shattered scores of Liberty ships. They traversed northern passages to Murmansk, delivering Lend-Lease aid to the Soviet Union, where near-freezing waters rendered Liberty ships perilously fragile. The Victory ship SS Hobart Baker completed 17 Murmansk voyages without developing any strain fissures. The Liberty ship John Walker, on the identical path, showed cracks during her second trip and was pulled from northern duties for good. Sailor spirits shifted dramatically upon moving from Liberty ships to Victory types. Post-war accounts gathered from veterans highlight the mental toll of working on vessels prone to unannounced disintegration. Seafarers described ongoing worry, particularly in low temperatures. Resting was tough amid every creak of the structure, possibly heralding a split. Certain crew members sought reassignments or outright declined voyages on particular Liberty ships with documented fracture issues. Victory ships rebuilt trust. Teams drove these hulls aggressively since they endured the abuse. That assurance boosted operational efficiency, quicker port reloads, readiness to venture in iffy conditions, and bold tactics during aerial assaults. The Battle of Leyte Gulf in October 1944 showcased the battle hardiness of Victory ships in scenarios that would have wrecked Liberty ones. 16 Victory ships backed the assault group, ferrying munitions, aircraft gasoline, and provisions amid kamikaze strikes in gale force weather. The SS Kyle Johnson absorbed a close bomb impact that warped her upper plating and fractured 3 support ribs. She pressed on, discharging loads while under bombardment for 4 days prior to pulling back for fixes. The built-in toughness and fracture-stopping designs prevented small harms from escalating to total collapse. Liberty ships facing equivalent wounds usually had to be scuttled as the splits grew uncontrollable. The financial math was harsh, yet obvious. A typical Liberty ship ran about $2 million in construction. Victory ships came in at $2.6 million to $6 million, or there's 30% pricier. However, a Liberty ship faced a 4.6% risk of total structural breakdown over her lifespan, drawn from documented incidents up to 1944. Such breakdowns claimed an average of 18 lives each and wiped out payloads valued at 3 to 5 times the build price. With Victory ships showing no failures, the extra $600,000 up front was offset in the opening half year of use alone, via slashed hazards and lower coverage fees. As the war wrapped up, merchant sailors shared a dark proverb that capped engineers grasped the distinction. Liberty ships were assembled at a rapid clip, sectioned off in large segments. Victory ships, by contrast, were crafted with meticulous detail, evaluated over extended periods. Those precise details, the deliberate order of welds, the rigorous oversight of quality, the strategic inclusion of crack-stopping features, ensured years of reliable operation rather than frantic hopes amid the hull's creaks in icy waters. In 1946, Bessie Hamill stepped back into everyday life quietly, with no public acclaim except for a note of praise from her shipyard foreman. She earned no awards, gave no congressional testimony, and never appeared in the scholarly articles that eventually chronicled the transformation in welding techniques she had ignited. The technical community integrated her practical wisdom, reframed it through equations and scholarly jargon, and presented it as originating from controlled experiments instead of insights gained by a welder on the graveyard shift. For years, manuals on welding described techniques for managing stress without crediting the individual who first spotted the need while seeing panels distort beneath her arc. Still, her influence echoes throughout contemporary engineering, extending well past maritime construction. Today's welded assemblies, whether towering buildings, oil conduits, or high-pressure containers, adhere to ordering guidelines that trace straight back to the methods refined at the Richmond shipyard in 1944. The American Welding Society's Code for Structural Welding, issued initially in 1947, established outward-from-center welding patterns and stress mitigation rules as essential norms. The pipeline projects spanning Alaska during the 1970s drew on welding approaches that cited Victory ship practices to avoid fractures in frigid Arctic environments. The 800-mile Trans-Alaska Pipeline, transporting heated petroleum across freezing landscapes, stands thanks to the knowledge Hamill imparted. Bridge engineering adopted these same concepts. The tragic collapse of the Point Pleasant Bridge in West Virginia on December 1967, claiming 46 lives, involved lingering welding stresses as a key element. Probes into the incident uncovered that welds done without correct ordering had trapped stress buildup in the framework. Subsequent updates to regulations enforced the ordering and verification steps that Victory ships had innovated. Since then, All welded bridges integrate those mandates. The 1990s upgrades to the Golden Gate Bridge for earthquake resistance, incorporating vast amounts of welded steel bracing, employed simulated welding orders to reduce leftover stresses. Advanced iterations of the experiments Hamill conducted manually with sample plates in 1943. The deep-sea petroleum sector has absorbed the wisdom through hard lessons time and again. The 1980 capsizing of the Alexander L. Kielland rig off Norway, which took 123 lives, linked partly to cracks spreading from welds sequenced incorrectly. The 1988 Piper Alpha rig blast in the North Sea, fatal to 167 workers, started from a fissure in a stressed welded joint. Investigations after each event scrutinized joining techniques, only to reaffirm basics validated by Victory Shipbuilding 4 decades prior. Current offshore guidelines now demand heat-based stress reduction for vital joints, mirroring the furnaces Kaiser set up in Richmond's assembly areas. The giant steel casings for nuclear reactors, enduring intense heat and force while housing fission processes, embody the pinnacle of these stress control methods in welding. Such enclosures must be free of any flaw-starting spots. Plans for welding reactor shells use digital modeling to predict heat impacts and stress remnants before any arc is lit. The full assembly then undergoes post-weld annealing in massive kilns, just like Victory ship components, to erase stresses that might lead to breakdowns. Designers in the 1950s drew explicitly from Victory ship practices as their core blueprint. Hamill's insight reshaped engineers' views on building processes at their root. Prior to Victory ships, planning and assembly operated in silos. Designers created blueprints, builders executed them, with little dialogue on how assembly choices influenced durability. Victory ships demonstrated that the order of assembly rivaled choices in materials or blueprints in importance. Today's engineering curricula treat production methods as core to design instruction. Students grasp that an ideal blueprint marred by flawed assembly yields weaker outcomes than a simpler one crafted correctly. The 5-day build schedule, though remarkable, wasn't the true triumph. Kaiser's facilities. They might have kept churning out Liberty ships at a frantic pace forever, sending out flawed hulls that appeared ready for the seas, only to shatter under strain. The true wonder lay in deliberately easing off the throttle to get things done properly. It took real guts to pause the assembly lines and overhaul the methods, drawing from a welder's sharp observation that flew in the face of long-held conventions. That openness to hearing out those on the ground, to concede that textbook engineering had overlooked a vital detail, and to reshape the entire approach based on hands-on evidence instead of stubborn preconceptions. That's what sparked the real change. Every contemporary production system, from Six Sigma and lean manufacturing to total quality management, weaves in that core idea. The person knee-deep in the workflow frequently spots flaws that elude the theorist crunching numbers from afar. Bessie Hamill passed away in 1987 in Sacramento, her death notice noting just her stint in the war-era shipyards. Yet in every fused framework enduring today, every conduit threading through icy expanses, every containment holding volatile energies, every span arching over waterways, they all bear traces of her influence through their carefully staggered seams and annealed connections. A quiet homage to the craftswoman who probed the reason behind the fracturing vessels and rejected the notion that that's just the way it is as sufficient.